We're going to talk about storage performance in general and what it may be basic for some of you. We'll get into SSDs, we'll get into tiering a little bit and what that does for SANs. I think Dave gave us a good solid foundation for SANs, and now we'll get into how do we deal with performance. I've been in the cells, the storage cells end of things for 13 years. Now, before that, for 20 years, I was a consumer of storage. I worked for 10 years, I worked for the group that did the student loans for the state of Utah, and I managed their data center. I also worked up at Evans and Sutherland when they were trying to build their supercomputer back in the heyday of the 90s. I've worked at Texas Instruments and Bank of America before I went and worked for a number of storage companies. And so I want to make this interactive, and so I want to make sure that any question that you have, bring up. There are no dumb questions, there are dumb slides. You'll see a few dumb slides on here. But let's make it interactive. If you have some questions, or I may not have the answers, but we can find the answers and get those to you. So performance in a SAN is always a compromise. You're usually giving up something. And this slide really doesn't show what in true fashion. I mean, it may show as far as speeds, but capacity-wise, this isn't a 7.2K. But you're always going to give up something, and it's always a compromise when you're talking performance. SSDs traditionally has been high cost in order to get into the SSDs. And a few years ago, it was really high cost to get in. And usually the 10Ks and 15Ks are going to be more per terabyte than the 7.2K drives. About a month ago, we're not actually in August. So here along the Wasatch Front, we've had the hottest summer on record. And so I decided to take the family down to Lake Powell, and we're going to do some boating and so forth. And so it's the middle of August. We go down there. The temperature of the lake is 80 degrees, and usually when we've been down there before, the heat is just so unbearable even at night that the rocks are just, you can feel the heat coming off from those rocks. We hit it at a good time because it was about 80 degrees during the day, a little bit of rain, middle of August, hottest summer on record. At night it got down to about 60. It's cool. It's cold actually. It felt cold. And we decided we were doing some wake skating and wakeboarding and so forth. And it was interesting. I had my sons, this is one son that's out doing some wakeboarding, and had another son driving, had a son-in-law in there. And they'd gone with me over to the marina to gas up the boat. And at $5.50 a gallon, they saw the price of that, and these are usually guys that don't care about price. It's it's what you can do and how much fun it is to do it. And so it was interesting. We were going along here. Okay, you're seeing the boat here off the side, and we're going along about the same speed, and then all of a sudden, this boat just really started going. I mean, this guy is flying. And the interesting note to this is my son-in-law turned to me and says, I wonder how much it costs him to fill up. Not that would be fun, and that would, but we didn't need this boat to do this. So it's always a cost. What are you needing to do? And what is it going to cost you versus the gain that you get out of it? What we'll talk about here this morning is we're going to try and define SAN performance as best we can. The latency, the causes, the interconnects, the disks, the servers, everything in between that creates SAN performance. The disk performance, SSDs, I mean, they're all the rage. Everybody we go into anymore to talk about SANs, they want to know about SSDs, and they think they need them. And in some instances, they may. But so far, I think there's only 1 or 2 customers we've gone to that have wanted SSDs where we could actually show them that where it might work or where it might fit in their environment. Mainly because historically the cost has been too high for what you get out of them, and they didn't need them. We look at their environment, and you know, it's like Dave was saying, need 2,000 IOPS. Well, you know, at 2,500 IOPS per drive, you're talking about, you know, ridiculous amounts of performance for the cost. So design too. What do I need? What do I want? What about tiering? How do you know what you need? How do you know what your environment looks like? Okay, so defining performance. So how, you know, what do we mean when we say performance in the data center? What are we talking about?
Bottlenecks, lag times, I/O.
I/O, bottlenecks, lag time, and where are those found?
They can be right.
They could be anywhere from the beginning of the server all the way down to the bottom of the SAN.
Or the application.
And that would be on the server. And they're poorly written applications, and we've seen enough of those out there. So how do you measure data performance? Now we're talking about data performance. Megabytes per second, IOPS, and latency. How do you improve it? Like someone said, you find those bottlenecks, and usually you throw hardware at it. But the important thing is to understand your application, which is what Dan mentioned, the application footprint. What is it needing? And what are you going to need for that? Because that's really what's going to define it. Now, megabytes per second, IOPS, and latency, they're all important in understanding performance in a SAN. Megabytes per second is the throughput. Throughput per second. It's measured in both read and write data. The IOPS are the I/O operations that can be done per second. And it, again, is measured in read and write. The latency is the average length of time that it takes for that I/O operation to complete. It's usually measured in milliseconds, and it's also both read and write operations. Applications, they only care about latency. They only care about latency. So if the storage system cannot meet the requirements of the application, then the required megabytes per second, which would be throughput, or the required IOPS, then you're going to have high latency, and your application's going to croak. So latency, usually less than 10 milliseconds, is great. Less than 20 is a good average. And in fact, most Microsoft applications says you need to see less than 20 milliseconds of latency. You can have spikes within your latency, up to 50 milliseconds, even higher, as long as those spikes are not consistent. And so then we get into the large block I/O versus small block I/O, and the whole goal is to minimize the latency. And so how do we do that? And how do we figure out what we can do to do that? The cause of latency could be on the server. It could be on the network. It could be a poorly written application. It could be that you design the drives that are on the SAN wrong. Who's complaining about the latency? Is it the array that's complaining? Is it the server that's complaining? Is the app? It's always the application that's going to complain, but where is it? Yeah, the end user. That's where you hear it from. Random versus sequential IOs. So we're going to talk about IOs, and this is key to understanding IOPS. Most workloads today are going to be random. Even if they start out as sequential, sometimes they become random. Examples of randoms are listed there, the databases, the email servers, and so forth. Examples of, yes?
Well, one thing that we can think about as well as we're dealing with a SAN that's going to be hosted in a virtual environment, you're looking at 40 database servers, 40 email servers. So even if a few of those are hugely sequential, like video streaming, you're still going to have random I/O as far as the SAN is concerned, because you're streaming 50, 60 video files all over the disk.
Exactly. And that was the point, that sometimes the sequentials turn into random. And that's where it does, is when you have multiple sets of sequentials running against the same set of drives, it actually turns into random. You'll see that like with backup software applications that will run multiple jobs, you know, that will kick off. A sequential operation then becomes a random because it's all over the disk.
And you can see it if you make even up to, like, say, 4 file transfers to a single external hard drive or something, and you watch the speed just cumulatively plummet.
Yep, exactly, exactly. So examples of sequential workloads, and this is the boot disks, the streaming video, and again, if you have more than one instance of it, it turns into random, the same way with backup and backup staging and so forth. So identifying your random and sequential workloads. Sequential workloads usually have a higher average I/O transfer size, so they're typically 64K or higher. Whereas your random workloads are usually less than 32, usually around 4 or 8K. They're usually associated more with the megabytes per second or the throughput on sequential, because it's not the IOPS on the back end necessarily. It could be, but it's usually sequential, it's not. And then you need to look at your overall picture, and you need to point out, when are you doing your backups? Because that's going to be a sequential, and you'll see that signature of those nightly backups within the range that you're looking at. It's going to be mostly reads, it's going to be large read I/O transfers, higher megabytes per second during that period of time that you're doing the backups. Usually happens after hours and so forth. Random workloads can have very high IOPS, but low megabytes per second. This is a telltale sign of the random I/O pattern that you normally would see. So the challenges of sequential workloads is true sequential workloads, not multiple different things going out and turning it into a random workload. They're uncommon anymore because we're doing so many different things to the drives. But backups usually, if they're not multi-streaming backups, it's usually a sequential workload, as mentioned here. But remember, with SSDs, they're great performance on random reads, and random writes and SSDs sometimes can be difficult. So sizing for throughput and IOPS. Okay, so how are we going to size this? How are we going to size the throughput that we need to create the performance we need on the back end? So you need to consider your sequential workloads, which may be few, because there aren't a lot out there anymore. But backups could be one of them. It impacts not only your disk choices, but your network in general, because that's what it is. It's the throughput that you're creating there. For most applications, the peak throughput occurs during, of course, your backup time. For SSDs, it's usually the throughput you need to size for rather than IOPS. And why would that be?
One drive will give you all the IOPS you need.
Yeah, we haven't hit the IOPS of an SSD, really. I mean, when you do multiple SSDs, you've got plenty of IOPS. It's that pipe, that throughput, trying to get it through to it is the issue. So sizing for random workloads is under the IOPS section there. It's also important to understand your read-write mix. And we'll talk about why that's important. How many reads versus writes do you do? In certain circumstances, writes are going to cost more than reads. The most common methods for improving performance that people do is adding more drives. In today's virtualized back-end environment, that's where you get more spindles, you get more performance. Okay. RAID policy. RAID 10 is the fastest thing out there, but it's not the most efficient that's out there. So if you want to write something, write it at RAID 10. It will be the fastest way to write. RAID 5 and 50 are slower, but they're still fast when you consider how many disk drives are involved. And RAID 6 is the slowest, but it's the most robust. And anymore, we're saying anybody that does a terabyte or more size drive should probably, and if it's 7.2K drive, you should probably do RAID 6. Mainly because then you're starting to play. You know, you're playing the gambling game. You know, are we going to be able to rebuild a drive before another drive fails? And so RAID 6 fits really well there. The faster drives, so you may go from a 7.2 drive to a 15K drive or to an SSD drive. So these are the most common methods, and also moving to a 10 gig environment across your network.
Hey Doug, RAID 10, is that just a couple of JBODs that are mirrored, or what is RAID 10?
RAID 10 is 2 drives that are mirrored together. And so your efficiency is basically cut in half, you know. And so that's why it's not efficient, but it's great for writes.
Well, it's even more than that too. It can be 2 RAID zeros mirrored together.
Yeah,
so
RAID
1, 2, 3,
yeah.
5 drives in a RAID 0, but then have a mirror of that.
That's what I'm saying, like it's basically JBOD.
Well, a JBOD is
No,
completely
it's-
different. It's like having a bunch of RAIDs. You know, they're all just independent.
If you're saying disk as meaning JBOD, then that's correct, yeah.
And JBOD's just a bunch of disks where
Yeah.
you can treat them as individual disks.
Right, but if they're mirrored, then that becomes RAID 10.
RAID 1.
RAID
You don't
1.
have striping.
Yeah, you have to stripe
It's
it.
having a RAID 0 of disks and then mirroring that to another RAID 0.
Yeah, RAID 10 basically is RAID 1 and RAID 0 together. They call it RAID 10. It's mirroring the striping.
So on the back end limitations of SANs, back and front end. The front end, we've got the iSCSI 1, which Dave, if it's implemented right, he's happy with. If it's not, he's very unhappy with. And like Dan says, we sell a lot of iSCSI SANs out there. And 1 gig iSCSI. And we're now selling a lot of 10 gig iSCSI out there also. But I mean, you have to take it for what it is. I mean, you're going to get about 70 to 75% actual theoretical throughput through the 1 or 10 gig iSCSI. And you need large blocks to even achieve this kind of stuff. So the performance is there, but the cost is a lot less, not only in coming up to speed, but also in the cost of the infrastructure that you have to put into place. So fiber channel, we're at 4, 8, 16 gig fiber channel. And really, it's pretty solid. I mean, you're gonna, if you got 8 gig fiber channel, you're gonna get close to 8 gig. You could, if you're pushing it. Again, you need the large blocks to achieve that. On the back end then, I didn't even put SATA on here because we don't sell it anymore. But I put SAS because that's really where we've we've come from and where we're going to, with the 3 gig and now the 6 gig. Does anybody have any questions on the front end and the back end? Front end out to the switches, the servers, and so forth. Back end are out to the drives. Okay, and you may even have. There are instances where you can have SAS on the front end too. So with 6 gigabit SAS, we've just completely improved our performance and opened up the world to SSDs. In other words, to really use the power what SSDs can do. With your 24 gigabits per second, then we can start driving some of those numbers that we're going to see in the SSDs. So in a 24 drive configuration, you get up to 70% improvement in sequential reads and 190% in sequential writes from just moving from 3 gig to 6 gig SAS. So 6 gig is, again, those 4 paths give us a huge improvement on the back end. So hard disk drives. This may be something you don't care about, but there's a seek time. There's a rotational latency, and there's a sustained transfer rate. And that equates to the number of IOs that a disk can do. And so with the seek time, it's about 4 milliseconds for your 15K, almost 10 for your 7.2K drive. The sustained transfer rate is the 125 megabytes. And with a 7.2K drive, it's about 100. So if you wanted to get an idea of what the performance on your drives are going to be, this is kind of a rule of thumb that we use. For SSDs, about 2,500 plus, it could go way up, just depending upon the application, how you're using those SSDs. Are you doing RAID 10? You're doing RAID 5? What are you doing there with them? The 15K is about 170, 180. 10K is 120. 7.2K is 80. Okay, and so the equation that you come up with the IOPS is you got the drive manufacturer. You get the information that you're missing from the drive manufacturer. Use this equation and you come up to about what you're going to get on the IOPS there. Are the numbers hard numbers? No. We've seen, 15K drives get 300, 300 IOPS out of a single drive. So, I mean, it just depends. But these are rules of thumbs that you can use. Throughput and I/O size. So this is again, we're back to the megabytes per second and the IOPS here. Throughput is measured by a number of different factors. And in the simplest form, you can calculate your throughput by taking your IOPS times your block size, and it will come out with your throughput. General rules of thumb is the smaller the block, the less bandwidth you're going to consume. And I know these are probably, duh kind of things, but these are things that you need to think about when you're doing it. The smaller the block, the more IOPS an application will perform. Larger the block, the more bandwidth and less IOPS it will need. Disk queue length. So this is another metric that you look at when you're looking at performance. And the disk queue length is the number of outstanding operations that are waiting to be completed. Lowering your disk queue can be completed in a couple of different ways. Increase the speed of the disk, go from 7.2 to 15K or 10K, or increase the number of disks that you have, the number of spindles that could go across. And when we virtualize on the back end, it's spindles or everything to performance. You need to really understand your applications and what you're trying to do with the disk queue. So this is a question. If the general rule of thumb is that the disk queue per drive over 2 is too high, then if a DBA is looking at a logical drive made up of 8 physical disks and his performance is seeing that the disk queue length is 10. Is that good or bad? What?
Seems good.
Good. It's just math, right?
Well, it depends if you believe in that kind of thing.
If you believe in math, it's just math. Why? Because 8 disks times 2 equals 16. The DBA sees 10. 10 is lower than 16, so it's below the threshold of pain. So disk queue length, again, is another thing to look at when you're looking at performance. SAN virtualization on the back end. And we're talking about not only virtualizing the disks across the back end, we're talking about virtualizing all the ports. We're talking about virtualizing the RAID and the controllers. Everything is virtualized on the back end. This is pointing out to the RAID, and you've got a volume that might be RAID 10, RAID 5, RAID 5.9, RAID 6.6, RAID 6.10, and you need to be able to, on the fly, go from RAID 10 to RAID 5.5. What's the fastest way to write to a drive with a RAID? What RAID is the fastest way to write to a drive? 10. How much does that cost you?
A lot.
Double.
Yeah. You've got the overhead. And so if you could take RAID 10, write it at RAID 10, and switch it to RAID 5 on the fly, going forward, then you've saved, you've written it at the fastest way, but you're saving the efficiency by moving it.
I don't understand the notation with the hyphen. So what's 5-5, 5-9?
5 drives.
Five drives, but in a virtual environment, this is the traditional RAID, 5.5, 5 and 5 drives,
Okay.
RAID 5 and 9 drives, or 10. So write at RAID 10 and move it down to gain your efficiencies back. So again, we're talking about true SAN virtualization from the top to the bottom. And this is key to it because when you write at RAID 10, again, you want to convert that down and recoup some of the efficiencies that you can have out of the tiering. So 80% of, let's say 80% of data is inactive, and this is something that Dave alluded to. Why is it on your higher tier drives? Well, because you have to physically move it to another tier if you want it down on a different tier. That's why it's sitting on those higher tier drives. How do you determine how active it is? Well, you can go out there and look at some of the reports or whatever and try and figure it out, and then you see that it's not being used and move it down. Why not move it through the tiers, the most cost-effective pool? I mean, that's the whole idea of tiering, is to get the data at the right place that's the most cost-effective. You don't confuse it with ILM, because that's with block level tiering, because they're two different, complete different things. ILM has to do with the files, okay, and how they're being accessed and archived. Whereas block level tiering really has to do with how the data is being read, used, and implemented by your applications. And then we know, okay, how active is that data?
That would be 3 layers.
That would be 3 layers.
I wonder who does it.
I don't know. We'll probably find out.
We'll find somebody.
Here are some of the trends that are going on in Flash. Flash appliances and Flash companies are just going crazy. I mean, we've got startups coming out of our ears on Flash type things. They're up over 100% year over year. But Flash costs are falling. They're falling faster than hard disk drives. But just because they're falling faster than hard disk drive doesn't necessarily mean that they're affordable. We're going to talk about affordability. So what about this one here? How big are hard disk drives now? 4 terabytes on the 7.2, but those are the slower drives. What about 15K? 600. That's the highest ones. What's the highest SSD now?
Just come out with 900s and 1.2. are those for?
10Ks. 10Ks, they've had 900s out. They just came out with 1.2 on 10Ks. So an SSD drive, 1.6 now. So they're getting higher than your fastest drive by substantial amounts, okay? That's on the MLC line. So the structured hot data opportunity, okay? Let's take it like this. This is going to be your SSD, your flash, I/O intensive, performance optimized here. This is really going to be your 15K, and cost optimized your 7.2K. This is what we're going to see going forward. We're going to see your flash increase. As the price comes down, it'll increase, you know, more over time. What is getting smaller?
Performance,
The 15K. And why would that be?
because SSDs will take the price.
Because this is helping your performance right here if you can afford it, okay?
Because most data is stale.
Because most data is stale. That's why this is so big. You're right, exactly. But to get the data there, you've got to have the performance. And applications want to see some sort of performance there too. So that's the trend that we're seeing going forward. Flash prices are declining rapidly. This is what we're looking at right now. Flash SSD is going here. The 15K. So it's still more expensive, 15K. But look here at 2017, they're saying it's going to cross the line. And the 7.2 will continue going down. We'll talk about a little bit later how you can get the flash for the price of drive. So instead of waiting till here, right here, you can already get flash for the price of HDD. The benefits of flash, I think we all know. The low latency, applications are happy, high performance. Flash can replace the 10K and the 15K for reducing that latency. I mean, that's the idea behind them. But here are some of the things. Okay, we're talking about CPUs, transactions per second. You've got your DRAM here, your PCIe SSDs, okay? So you're looking at transactions per second and then going across here. So this is what? Who's the company that does a lot of that? Fusion IO. Storage SSD, that's what we've been talking about as far as the SANs, and HDD. So designing for SSDs. Okay, where are you going to start? Go ahead.
So I just haven't kept up on this kind of thing, and I know it's an issue, and we talked about it a little earlier, Dave, but what's the impact of SSDs wearing out? How is that actually affecting us in real world applications?
And we'll talk about that. As soon as we'll dive down into that. Just wait for a couple of slides and we'll get right to that. And that's a good point because they do wear out. There's an issue there. That's one of the drawbacks to it. But when you're going to design for SSDs in your environment, you've got to know some things, okay? You've got to know what your application needs are there, what your I/O load is, and what it's going to be placing on the system. You either need to get some perfmon information, some I/O stat data, or you have on your thing there a DPAC done. And we'll talk a little bit about that later. You absolutely need to understand your megabytes per second in your IOPS, in your environment, before you can design a SAN, let alone design for SSDs. So you analyze that data for IOPS and megabytes per second, and then you can decide if you need it. If it's 2,000 IOPS that you need and less than a gig per second for throughput, you probably don't need SSDs. They're probably not even cost effective right now, depending on the capacities or how much you need of it. And your throughput is 24 gigabits per second. So the future, okay, what's coming out in the future here? PCI SSDs, fluid cache for SAN is what Dell is talking about. And this is just one aspect of what's coming in the future. Right now, today, you've got your servers coming down through your storage network to your SAN, whether it be iSCSI or Fiber Channel. Dave has his choice, it would be Fiber Channel for him. I think he made that clear. iSCSI, seriously, works. And if you implement it right, the cost, you know, if you're just a small company coming up, if you have the money and you want a rock solid, go with Fiber Channel. Absolutely. So this is an environment that you're seeing right now. So what if we were to add some cache software here, and then we add a PCI SSD card in your servers? Well, what we're doing here in the future is we're creating a private cache network. And rather than always coming down to the SAN, we may be using these SSDs across servers for a type of cache, a type of a tier of storage.
But then you do have this write latency problem to your main storage, right?
But you don't have to worry about that because it's already told the server it's done, and your writes are not. You don't have to write here as much because your writes are going to your SSDs up here. Plus, this server right here can use this PCIe's SSD because of this private network.
Now, is that going to be iSCSI or is that going to be Fiber Channel?
It doesn't matter because at the end, right here, it doesn't matter because here's where your iSCSI or Fiber Channel connectivity is.
No, I'm talking about like a private cache network.
Well, this is a software network. This is a company that Dell bought a number of years ago. And so you're going to be able to cross servers, use this PCIe cache with very low latency and do some amazing things with performance.
We're going to call that tier 0, guys.
That's the other key point to it. If you don't have true tiering, if you don't have a way to tier through multiple things and move data down, then none of this really makes any sense because it's a management nightmare to sit and move the data yourself. But with tiering, again, you're going to be able to tier from here to here to here to here to here to wherever, all the way down through. But your performance is going to be great because most of it's going to stay up here in your private network. So, because I like the bouncing balls, I left that in for this slide. It doesn't mean anything, but I thought it was cool. So tier 0 is either flash in the server, the flash on the appliance side of things. You can have your write intensive, whether it be 15K or 10 or SSDs. What about having a write intensive SSD and a read intensive SSD as part of your tiering? I'll get rid of the balls here. The attributes of SSD, let's talk about that next. It's really best at random operations and it's great for writes. But it's measured in IOPS. It's order of magnitude higher. I mean, it's just huge with what you can do with SSDs. Sequential operations, it's fine, but it's less impactful. And you have to determine the cost for what you need. And again, I think we're getting down to the point that we talked about before is there's not a lot of sequential operations anymore because people are doing multiple sequential operations which then become a random operation. This is what they look like. Bunch of moving parts, no moving parts. The advantages and comparisons, SSD's advantages over hard disk drives, no moving parts, lower power, much higher IOPS, so fewer drives are needed. The hard disk drive advantages over the SSDs is it's a lower cost until now, and we'll talk about that.
What about heat?
What's that?
Heat.
Heat is another thing. It's the heat, the cooling of it. You're right. The SSDs are environmentally are going to cost you less. Higher capacities with the 7.2K drives only. Your 15K, you're already out doing them here with your SSDs.
Can we go back to that?
Sure.
The second point from the bottom.
Data retention is much longer.
And that goes to your point.
And we'll talk about that with SSDs. When you first start a new SSD drive, your data retention with the drive not powered is measured in months, maybe years. When it gets towards the end of the drive, it's measured in weeks.
So on an SSD, I write something to it and then don't power it up, don't touch it, it's going to fade away.
It will fade away.
Just like your thumbsticks.
Yeah,
I didn't know that about thumb drives.
yeah. So I'm glad you mentioned that. And we'll talk a little bit more about that, but not necessarily, not a lot. But endurance, I mean, that's the whole idea of the SSDs is what is the endurance on it? And what does it cost you to have that endurance? How long will it last? What's the wear out factor? And the number of erase and write cycles that are going to be available on that SSD. Are we talking about SLC or MLC? And I'm in general talking about enterprise drives here, so I'm not even going to talk about the consumer stuff. Retention, how long will it retain power, to your point, after it's off? Usually multi-years early in the life of the drive. But towards the end, it's about 3 months. But they're continuing to make improvements on that, and they'll continue to get better at that. So let's talk about the SLC and MLC. SLC, single level cell. That's why it's SLC. Multi-level cell MLC, okay? SLC and NAND offers relatively fast read and write capabilities. It's got great endurance. Endurance meaning keeping the data for you. And it has error correction algorithms, but there is a cost to it. MLC you usually can get higher capacities on MLC. Like I said, 1.6 on the MLC now, whereas our highest on the SLC is 400 right now. In the same size, it comes at significantly lower cost, so it costs lower, the MLC. So what about overcoming the write challenges as SSD? Because really that's the Achilles heel for SSD, is the write performance. When you write to a flash cell, it's a two-step process. Do you know that? You have to erase and then you have to write. And so one thing that Dell has done, and I'm sure there are others that do this also, but I don't know who they are, but we not only over-provision the drives at 28%, which was talked about earlier in Dave's presentation, but we also pre-erase. So in other words, you no longer have to erase and write, you can write. So it eliminates one of the steps, thus increasing the writes of your SSDs with a pre-erased scratch pad. And this right here is just showing the size actually determines the time to read and write on the flash.
Hey Doug, quick question.
Sure.
Does the Dell architecture take any performance hit for that feature of pre-erasing? When does that happen?
That happens before the drive is implemented.
Oh, all right. So no impact at all.
Is that on your MLC or just your SLC?
That is on the SLC. And so and we're focusing, what we're saying is focus your writes on your SLC. They cost more, they're faster, they're better endurance, and focus your reads from your MLC. And this is why. Not all the SSDs are created equal, but the enterprise SSDs all have this. Okay, they have the dual port for high availability and better performance. They're going to have some sort of built-in wear monitoring. Are they better? If you're buying an SSD array and they don't tell you what's going on as far as your wearing on those drives, you could be in trouble. So you better have some sort of way to monitor that wear. The over-provisioning that we had talked about, we have some non-volatile cache on each drive, a little bit of non-volatile cache, and full end-to-end protection with error code corrections. So what we're saying here is with your write-intensive writes, we're going to use the SLCs. And their capacity, as I mentioned, is 40 gig. Your endurance, you can do 30 full writes a day. Written in petabytes, 21.9 petabytes per drive. So they're great for writes, but they're expensive again, and your performance and your write bandwidth. Okay, compare that to
From simple math, and tell me how many days is that?
save me from simple math. I don't know. I don't know. It depends on how much. It depends on your writes,
We're
right?
talking full writes a day.
30 writes, certain times 400 gets us to 22 petabytes.
So here's your MLC. Now, if you're being sold a bunch of MLCs and that's all you're getting, this is what you're getting. Okay, you may get a higher capacity drive. You may or may not. Dell now has the 1.6 terabyte drive. But for your writes, you only get 3. So you can see the endurance already between the two. But these cost less. And then the performance all the way down to the write bandwidth here. So
It means 3 writes per day means I can write over that disk every 3 times a day, not just 3 writes. I could
right, go through the whole
thing.
drive.
1.6 times 3 would be 4.8 terabytes.
But you can see that, and this is not a Dell thing. This is MLCs and SLC for the enterprise drives. It doesn't matter whose you get, but this is what it's going to be like. So what we're saying is this is really great for reads. Not so good for writes necessarily, but it's great for reads. This is great for writes. Write really fast. You can read really fast. So the other thing you got to remember is with SSDs, and I think this is probably out of place, but anyway, when you get to a certain point with regular drives, hard disk drives, you're going to hit the capacity of the controller, the memory, and everything in the system. You can only have so many drives behind that set of controllers. It's even going to go up steeper when you add SSD. So you got to be aware of that. Okay? Data progression is key to making this whole thing work. True data progression at the true block level. So there's the idea of multiple tiers of SSDs. So you have your read intensive and your write intensive. And what you'll do is you'll take your read or your write intensive and you'll write everything to your write intensive, which is smaller drives, but very high endurance, can do a lot of writes. And then you'll tier that off down to the read MLCs that cost less, but as a read device, they're great and they're very fast. And then as it gets stale, move it off to 7.2K.
One of the problems that we always have with these SLCs, guys, is that we just got the 400s announced. They were 200s, so you had to buy a lot of them. Even if you're using tiering, they would fill up so fast. How do you flush it all out and get it out of there so you can still have that great write performance? That's been an issue. Now at the 400, that's gone away a little bit, but again, using tiering and being able to change the RAID levels on the fly and move from SLC to MLC takes that away. So I can still have very fast reads in in solid state drives, but I can do it at a cheaper cost and higher capacity drives. Well, before to be able to do that, I had to buy a freaking tray of SLCs, which were at $4,000 a pop, was a lot of money, right? Just for the drives. So this is going to take some of that cost and that pain away.
So we're saying there may be a better way to optimize your way. All flash arrays, or possibly a mix of your read and write intensive, because it's gonna reduce your costs across the board.
Your write SLCs, do you tier the data out of that on the fly, or do you have to do your 24-hour period?
Good question. We'll talk about that too. It'll come up here in another slide. And it's there with 6.4, they're changing that so that you can actually do data progression on the fly.
And more than 100 days, so that's
Right.
this stuff.
So just to give you an idea, a rack 26U of 15K drives, okay? And what we've been talking about, a mix of your tiered flash, 1 tray, 2 controllers, 6U. With flash, you get, of course, a smaller rack unit, 50% more IOPS with this one, and 90% latency reduction with this one.
And no SANA in your server room.
That's right. That's right. Okay, so I mentioned that you better have a way to understand how your drives are wearing out. And this is one example of the way at least we're doing it, to show, okay, where is the wear? How are we? Which drives are wearing out? And how is it wearing out across the board? Tiering, okay, how do we move that data progression? Now we have on-demand data progression. So you still have your replays, and you could do on-demand hour by hour. And you can do your usage data progression right here. That's based upon your 12 down and 3 up. But with the ability to tier SSDs, you have to change the way progression is going to go, and this does it.
I missed about 12 and 3 lanes.
12 down, so after 12 days, if you're using the usage data progression, in other words, it's looking at your data at a block level, and it's telling, okay, how often is it used, you know, access, whatever, and it understands from the block level where that data, whether it's hot, whether it's still being used or not. If after 12 days, it'll move it down. If hotness, it'll move it up. That's your usage data progression. What we're saying is with this new SSD tier that we've got in here, we've got this on-demand that allows you to do it multiple times a day.
It takes 3 days to move hot data up the tier, even if it's accessed 100 times a day?
It depends on the access. It depends on the access, and it's an algorithm that's beyond my capability of trying to explain or even know. But you don't want the ping pong data either, you know. So you can understand there's got to be some, you know, mechanism to determine, okay, when is this really hot, or did it just get hot for an hour, you know? Because reading off 7.2K drives is not much different than reading off 15K drives. It's the writing to those drives that are the problem. Let me go back here. Okay, so SLC alone, this is your cost per gigabyte. SLC and MLC, the red here, drops it down to here. Substantial drop when you add an MLC to the mix. SLC, MLC, and 7.2K. That's this right here. This is 15K only. At a certain capacity, in other words, you just have 15K drives, okay, the cost per gigabyte is this much on 15K drives. What we're saying with SLC, MLC, and 7.2K, if you get to a certain capacity, there's no difference. And the 7.2K only. So, in summary, all SSDs are not the same, obviously, and they're all used for different purposes. SSDs are not saving the world, you know. They're not the panacea. But when using multiple drive options with the intelligent tiering, it can reduce the cost of implementing flash in your environment. It helps you, you need to understand your application to understand where the bottlenecks are. And the algorithms and SSD technology will just continue to get better. They're making huge strides in flash, and we're going to just see that go up. Storage strategies now, their report of enterprise use for solid state flash memory. It's my one Dell slide. We're the highest users of flash are Dell customers at 31%. Where do you go from here, okay? We've talked about performance, we've talked about what makes up performance, what you need to know about your environment in order to understand your performance. This is one of the ways that many people determine what they need. You know, when they're trying to find a SAN, it's kind of like, well, I think I need this or that or whatever. Nothing is used to determine really what is out there and what you need to create your SAN. So you have in your sheet there a DPAC sheet, and it's Dell Performance Analysis Collection Kit. And so what TNS is offering is for you to have a free DPAC done on your environment. It'll produce a nice report, but a couple of key things. It's lightweight. You don't load this on your servers. It's run in memory, runs for 24 hours. It's agentless. Go ahead.
I'll be your
Okay.
guiding point.
Good.
I actually did it.
How was it?
Did it on my VMware vSphere host.
What'd you think of the report?
So awesome. It was actually so easy that I want to do it again because I liked it.
Yeah.
And my situation's changed. I'd like to see what the new numbers are.
Well, let's do it. Let's get with one of the TNS folks, or Dan or I, and we'll get you the collection. But this is the kind of report it gives you, and let me give you a little more detail here. It goes out, it does the aggregation of all the servers that might be touching a SAN. You don't have to have a SAN now. In fact, it's designed to try and figure out what would you need in a SAN if you needed a SAN. Goes out to all the servers that would be touching the SAN and gathers the information that's already out there. Doesn't affect your performance, so anything, your servers or anything that's out there, it's just gathering data that your servers are already producing. Does a nice report, gives you an idea of reads, writes, your IOPS, your megabytes per second, your memory. It goes down into the disk queues, the memory usage on your servers, average I/O slots of your top 10 servers in your environment. It will give you a single page on each of the servers also. So we now know what we need to do to get performance, okay? It's all based upon latency, IOPS, and megabytes per second. The only thing you need to do is find out what is yours, and you can do that through perfmon, IOStat, whatever it is, tools you want to use. You can also request this from TNS or from Dan and I. We'll get this to you, produce this report, tell you what your environment's like.
Now, a couple things on